Well, thank you very much to the organizers for organizing this conference. It's great to hear everybody's work, and especially thanks for making effort to make remote participation possible. It's really been wonderful to be able to participate in this way. So today I'm going to talk about the Gemini LIGHTS survey. It's a survey of Herbig and T-Tauri stars. It's great to have a great introduction by Christian beforehand, because instead of looking at the lower mass stars, this survey is going to be concentrating on the higher mass stars, which have been largely neglected by surveys. So we're going to be looking at the higher mass counterparts to what the wonderful introduction Christian had talked about earlier. So to give a quick overview, we're talking about the same type of structure we had previously talked about. So we're looking at protoplanetary disks that have left their natal cradle. We are going to looking edge on. We're going to have a star with a disk that's going to extend hundreds of AU. It's going to be composed of large dust grains and small dust grains. And the small dust grains are going to be coupled to the gas, and that gas is going to have a flare shape of some height. And by using high contrast near infrared polarized imagery, we can trace the surface features of the disk, in particular the small dust grains, and that can reveal really interesting substructures. I think what's really important with polarized imagery is not only do you get to see the small dust grains itself, but you can also see shadowing or self-shadowing of the disk, which really reveals a lot of great information about what's going on in the inner regions of the disk that can occasionally be hard to access. In addition, and what will be really important to this work is that since we're looking at more massive stars, they are more likely to have binaries. And since our high contrast near infrared imaging is going to be sensitive to those companions. And so by taking all this information together, we can see, does the scatter light flux we detect for our targets correlate with disk and stellar parameters, so we can constrain planet formation. So the Gemini LIGHTS survey, or the Gemini Large Imaging with GPI, Herbig and T-Tauri survey, is a survey of 44 protoplanetary disks. These are observed with Gemini Planet Imager when it was mounted on Gemini South telescope. It's since been removed. All the images are in polarized light in J and or H band. And as I said earlier, it's going to probe a higher mass of stars than previously studied. So previously, the highest mass protoplanetary disks that were imaged in scatter light ended around 3 solar masses, and we're going to go well above 3 solar masses. Another way that we chose to select our sample was with a color diagram. So this is WISE2 minus WISE4 in the infrared and J band minus WISE2 on the x-axis. And by using these colors, we can probe the broad SED shape of our objects. So for example, down here will be your full disks, where it's going to have a continuous SED shape. And as you go upwards, you're going to start to have gaps and holes in your disks, going up to transitional disks. So by picking targets that fill in this color diagram, we can select a broad range of targets. Because what we didn't want to do is pick our favorite, best, and brightest targets, but we wanted to pick ones that may have not been studied as much previously, though we will still have some of our favorites in there as well. So the data products that we have first are the point sources. Because we're looking in near infrared high contrast imaging, we can look for point sources using ADI and Loki algorithms. We end up finding 24 point sources of 22 or around our 44 targets. This isn't surprising given that we are looking at a higher mass range of samples. 22 of these 24, given their position and brightness relative to the star, are consistent with being binaries. Some of these have been previously seen before, but others, given how bright in separation they are, it's a very strong assumption that they are likely co-moving with the objects. Though a few of them, the brown dwarfs and will need to be verified later to show that they're co-moving. But the majority of our data products is polarized light. So shown here in this image, all the light you're seeing and red is light from the central star that's scattering off the small dust grains and coming to us as the observer. And we're observing the dust around these objects. So one of the surprising things that we found, which was great to find, was a new planetary mask candidate. I've redacted the name here because we have submitted the paper, but it has not yet been accepted. So this is a 13 mass Jupiter companion. It's separated about an arc second, so it's quite a ways away from the target. It's very young system, and given its age, separation, and mass, because the star itself is fairly massive, it places really unique constraints on planet formation. So it's going to end up that this object itself is going to be great for future studies and for brown dwarfs and planets forming around high mass stars. But moving next to our polarized light, we've detected around 44 of our targets. We found that 80% of our targets, we detect some form of polarized light. We see a wide range of structures within our disk. We see a lot of continuous or fairly non-structured disks. Over here, we see our typical rings that we expect to see. We have what we are going to end up calling irregulars due to their structure. Some of them have been highlighted already in this talk, this conference, such as FU Ori, or located here, or GW Ori, which Stefan Kraus did a great paper on about disk tearing. And then some of them we detect we do not resolve enough to really say anything about the disk structure itself, but we definitely detect some form of polarized light. So taking all those disk structures, we're going to classify them using a modified Gruffy et al. 2018 that they used to classify these objects. We're going to have spiraled, which obviously have spiraled arms, irregulars, which I had previously talked about, continuous, basically we do not see in the scattered light any gaps or holes, rings, or we're seeing dust rings. The inverse would be to say that we do see gaps and holes for those. Undetermined, basically meaning that we detect polarized light, but there isn't a significant amount to say about the disk structure, and then non-detections where we don't detect a significant amount of polarized light. So we're going to take all those disk structures and plot them on an HR diagram. And this is an easy way to compare our disk structures we see with the stellar properties. I've plotted on here the zero age main sequence, the black dashed line. The color lines here are constant mass contours. So for reference, on the right, it's going to be younger. On the left, towards the main sequence, it's going to be older. And then on the right, it's going to be younger. And looking at our 6 categories, for the broad part, they're fairly intermixed between mass and age. We don't, broadly, for the most part, we don't see too many trends. We see unresolved, there are more unresolved and undetected for higher mass objects. This could be due to a couple factors, one being that higher mass stars are going to have a larger luminosity and can dissipate their disk. They also tend to be a little further, so we are not necessarily going to be resolving as much of the disk. So that could be one of the reasons we see a lot more unresolved objects for higher masses. But one of the key trends that we see are rings, which are the pink circles here, and all of them are located in the bottom right of this diagram. And in fact, for less than 3 solar masses are the only systems in which we detect ring systems. For the higher mass objects greater than 3 solar masses, we do not detect any rings. Rings are important because they're thought to be one of the key signatures of planet formation, where you have a planet located in this gap, carving out all the dust and gas, creating this ring structure. And so not observing any rings at higher masses is indicative of potentially planets struggling to form at higher masses. It could also be the fact that they do form, but they don't necessarily form the rings that we're seeing. We could also potentially be seeing a slight distance effect too, where we're not necessarily resolving as close to the star as possible, though given the size of some of these rings, we resolve them for these higher masses if they were around those stars. So further observations are absolutely necessary to search specifically for rings around higher mass objects greater than 3 solar masses to see if we can detect any trends in that regard. And then finally, we looked at summing the total amount of polarized flux around all our images and divided by the flux of the star. And this will give us an idea of how much, a distance independent variable of how much flux we detect around our given object. And we observe a trend that had previously been seen where for bluer objects, so on the x-axis is WISE2 minus WISE4 bands in the infrared. This trend had previously been seen where you see very little polarized flux around bluer objects, but when you go towards redder objects, you tend to see a lot more polarized light. This has broadly been interpreted as that you're going to have strongly flared or gapped disks over here where more light is allowed to shine on the outer disk, and therefore we get more polarized flux. Whereas down here, you're going to have more self-shadowed or flattered disks where less light is allowed to shine on the outer disk due to inner disk structures or the fact that it's a flatter disk causing less polarized light. However, with this trend, we also see an incredible amount of binaries. So any of these markers that are filled in or partially filled in, that means that there's an outer binary we detect in our sample. And we find that there are a lot more binaries on the bluer side compared to the redder side, suggesting that binarity plays a significant role in this, in determining how much polarized light our objects are detecting. So binarity is playing a role, potentially influencing the disks and what we're seeing. So going forward, including binarity is going to be a really important part in studying planet formation around these disks. So in conclusion, we detected 80% of polarized light around our 44 targets. We found a new planet candidate. We only found dusty disk rings for systems less than 3 solar masses. And we found outer binary systems are a really important indicator for the amount of polarized light that we're seeing, potentially complicating the previous story that we had for the scattered light and protoplanetary disks. So thank you for listening, and I'll happily take any of your questions.
Thanks, Evan. Any questions for Evan? No. Okay, go ahead.
Hi. Do you have plans to populate your HR diagram with another long-term program or something?
Yeah, I think Gemini, we don't have definitive plans right now, but what I'd like to do in the future is to, the GPI instrument is being refurbished and will be mounted on Gemini North. And so we can do a similar study in the North to also populate, especially the higher mass region. One of the difficulties with studying these higher mass stars is that they're typically not associated with the star forming region just due to their rarity. And so that will open up a large portion of the sky to further populate the HR diagram.
I have another question. In the planet candidate, there is these blue streaks next to the red dot. What is that?
Yeah, so I guess quickly, that's just an artifact from the data reduction process itself. So you're trying to remove the point source function from the planet, and that smearing is very typical for removing it through an ADI process. So it's a reduction artifact.
Okay, thank you.
We also have a question from the chat. So Rene says, is there a relationship between binary and stellar mass, or would that drive the color dependence you pointed out as well?
Yeah, that's definitely a factor. So because we find more of our more massive stars tend to have more binaries, So that's also true, where our more massive stars tend to be in this bluer category. So that definitely is, a lot of these factors are very intercoupled with age, stellar mass, and binarity.
Okay, perfect. Are there any other questions? Oh, yeah, go ahead.
Thank you for the talk. I think it was on slide 6 where you're talking about the disk classification of your sample. And is it coincidental that a lot of them look like the disks are viewed face on, or is, on the contrary, was that more of one of your selection criteria for your targets?
No, so there is that we did not select for face on. Some of them are, only a few of them are face on, like here. We have a lot of edge on disks here and here. So it wasn't a selection criteria.
Any last questions? So I don't see any. So let's thank Ivan and all the previous speakers again.